ఇక్కడ స్క్రీన్ బేసిక్గా
ఆ,
స్క్రీన్ వచ్చేసి
అని అడ్వాన్స్ కొట్టాను. అడ్వాన్స్ కొట్టి షేర్ కొట్టేసాను డైరెక్ట్గా. అయితే ఇది కొట్టకుండా వస్తాను.
ఈ పోర్షన్ ఆఫ్ ద స్క్రీన్ కూడా
Hello, good evening. Are you able to hear my voice? Is it audible? Good evening. Yes, audible. Okay. Let us start the class. Now, before going to start the today's class, just we go back to the previous class and we discuss about what we have done in the last class. What we have done in the last class. Last class is the first class for linear algebra topic. In the linear algebra, there are 5 subtopics. Very first one is determinant, second one is inverse, third one is rank, linearly independent vectors. Fourth one is solution of system of linear equations, and the last one is eigenvalues and eigenvectors. These are the subtopics, 5 subtopics in linear algebra. The weightage of this linear algebra is 1 to 3 marks only. You may get 1 mark, 2 mark, or 3 marks. Sometimes you may get more than 3 also. And we have started the first subtopic, determinant of a matrix. In the first subtopic, determinant of a matrix, already we have seen how to find the determinant of second order, third order, fourth order matrix. And whatever we have discussed the method for fourth order, we apply the same method for next higher order only. That is, whatever we have the method for fourth order determinant, we apply the same method for all higher order determinants only. That is expansion method, general method, just like first method of third order only. To write the third order determinant value, we have seen 3 methods: method 1, method 2, method 3. But method 3 is Kelsey method. Don't use that method. Just go to the first method or method 2 only. You can use method 1 or method 2 only. After this, we have done some problems, and after the completion of problems, we have discussed the properties, 10 properties, and then we have started the second subtopic, inverse of a matrix only. In the inverse of matrix, we have written some definitions: minor of element, cofactor of an element. Next, the cofactor matrix, adjoint matrix, singular matrix condition, non-singular matrix condition. Next, inverse of a matrix. After that, we have written some note points, the standard note points on or standard results on. Up to here, the last class. The last note point is for skew symmetric matrix. Whenever the skew symmetric matrix is given, check its order is even order, odd order. If it is odd order, if you find the determinant of the odd order skew symmetric matrix, that's its value will be 0 only. If you are given a skew symmetric matrix with odd order, then the determinant is always 0. Or every odd order skew symmetric matrix is always singular because determinant is 0 only. Okay. Now, up to here, last class. So let us start with today's class, continuation of the last class. We do the problems on inverse of matrix. After completion of problems, we start the next subtopic, rank of a matrix. Let us study problems on this. Problem number 1. The inverse of a matrix A equal to 2 by 2 matrix with elements 4 plus 3i. Here this is minus I. This is plus I. Next 4 minus 3i, comma, where I square equal to minus 1, comma, is. Matrix elements, and we are asked to find its inverse. Finding by this variable only, because that we have the formula. This matrix, one of the element is 4 3i, where conjugate sum. The number of this form, then this form complex number only. At least one of the element is imaginary or complex number, then such a matrix is complex, then such a matrix is called complex matrix. So we are given 2 by 2 complex matrix and we are asked to find its inverse. To find the inverse of the matrix, the given matrix should be non-singular. So let us check whether the given matrix is singular or non-singular only. Now, determinant of a 2 by 2 matrix equal to 4 plus 3i minus I 4 minus 3i, which implies determinant of a equal to product of diagonal elements minus product of non-diagonal elements. The product of diagonal is in the form of a plus b into a minus b form. 16 minus 9 I square minus 1 minus minus plus 16 plus 9 25 minus product of non-diagonal I square minus minus plus 1 equal to 24, not equal to 0. Matrix is non-singular, so inverse exists. We can write inverse of the matrix only. Therefore, A inverse equal to, using adjoint method, inverse is given by adjoint of A by determinant of A. This is equal to 1 by 24 into 2 by 2 matrix adjoint. Already we know the method of finding the adjoint matrix for 2 by 2. Without finding the minor and cofactor of each element, we can add the adjoint matrix directly for 2 by 2 matrix. Just we interchange diagonal elements. 4 minus 3i, 4 plus 3i, and then take the minus sign for non-diagonal elements. Minus sign for non-diagonal elements. Minus I becomes plus I becomes minus I. This is the inverse of the given matrix. It is a 2 marks gate question only. So from the inverse of matrix, we have a problems on inverse of 2 by 2, 3 by 3 only. Inverse of 2 by 2 and 3 by 3 matrices only. This is a 2 marks gate question. Next, problem number 2. The inverse of the matrix, inverse of the matrix A equal to 3 by 3 matrix with elements 2, 3, 4, 4, 3, 1, 1, 2, 4 is like previous problem. Here we are given 3 by 3 matrix and we are asked to find its inverse only. It is 3 by 3. First problem is 2 by 2 only. Again, you have to check whether the given matrix is singular, non-singular. Now find out the determinant of this matrix. To find the determinant of 3 by 3 matrix, we can use method 1 or method 2, any one. Now tell me the determinant value. Find the determinant and tell me the value. Okay, you got it. Determinant as -5, right? -5 is correct. Determinant of A equal to -5. This is not equal to 0. Determinant of 5 is -5, not equal to 0. So the given matrix is non-singular. The given matrix is non-singular. We can write the inverse of this matrix by finding the adjoint matrix. But to find the adjoint matrix of this 3 by 3, we require the minor of each element. Next, cofactor of each element. After finding the cofactor of each element, Using all the cofactors, we write a new matrix. Such a matrix is cofactor matrix only. After that, we take the transpose. The transpose of cofactor gives adjoint matrix. Adjoint matrix into 1 by determinant is inverse of matrix only. It is a method. It is a 3 by 3 matrix. Its inverse is also 3 by 3 matrix. Now, without finding all these means without finding the minor of each element, cofactor of each element, cofactor matrix, and adjoint matrix, we write adjoint matrix directly. Now here I will show you how to write adjoint matrix directly only. If A is 3 by 3, its adjoint is also 3 by 3, inverse is also 3 by 3. Now to write the 3 by 3 adjoint matrix for given 3 by 3 matrix, first we have to write a new matrix. We have to write a new matrix of order 4. We write a new matrix of order 4. From that fourth order matrix, we write adjoint matrix directly only. First, we write a fourth order matrix from the given matrix. To write the fourth order matrix, we require the 4 rows and 4 columns. To get the 4 rows and 4 columns, just observe the given matrix. In the given matrix, let us consider second row, second element. Second row, second element. Once again, I write here the 2 by 2 matrix. 2, 3, 4, 4, 3, 1, 1, 2, 3. It is a given 3 by 3 matrix. Consider second row, second element. And start here. Start here. Move in anti-clockwise. Move in anti-clockwise and come to the same position. Start at 3, stop at 3 by moving in anti-clockwise direction. Consider second row, second element. Start here, move in anti-clockwise and complete one cycle. After completing one cycle, we can collect 4 elements. 1, 2, 3, 4. That is 3, 1, 4, 3 only. After completing one cycle, we collect the 4 elements and we write the 4 elements as first column in this fourth order matrix order. Once again, I repeat, in the given matrix, consider second row, second element. Start at the second element, move in anti-clockwise and complete one cycle. After that, we can collect the 4 elements. The 4 elements are like this. Start with the second element, second row. That is 3, next 1, next 4, and then 3 on it. These are the elements. Consider second row, second element. Start here, move in anti-clockwise and complete one cycle. After this, collect the 4 elements, write the 4 elements as first column in the 4 by 4 matrix. Okay. Next, after this, we go to the next row. In the next row also, start with the middle element and do the same thing like above. In the next row, start with the middle element, do the same thing like above. Start here, move in anti-clockwise and complete one cycle. So that we can collect 4 elements. Write the 4 elements as second column in this 4 by 4 matrix. That is 2, 3, 1, and then 2 on. 2, 3, 1, 2 only. After completion of this row, we go to the first row. In the first row also, start with the middle element. Like previous 2 rows, we color the elements. Start here, move in anti-clockwise and complete one cycle on it. And collect the 4 elements. Write the 4 elements as next column. That is 3, 4, 2, 3 on it. Start with the middle element, go to next element 4, next 2, and then same element 3 on it. All the 3 rows are completed. After completion of all the 3 rows, again come back to the same starting second row only. We are starting with the middle row and we are moving like this in anti-clockwise. Again, we are coming back to same second row position. But for second row, already we know the elements along the first column. Already we know the elements for this as a first column in this. So that is why start with the second row, then go to next, and then repeat the first column as last column. Once again, I repeat, in the given matrix, consider a second row with the second element. Start here, move in anti-clockwise and complete one cycle. Collect the 4 elements, write the 4 elements as first column. After this, go to next row. Again, start with the middle element, move in anti-clockwise, complete the cycle. After completing one cycle, collect the 4 elements, write the elements as second column. Then go to the first row. Again, collect the 4 elements, write the 4 elements as third column. After completion of 3 rows in the given matrix, repeat the first column as last column here. That is for second round. 3, 1, 4, 2, like this. Writing a new fourth order matrix is completed from the given matrix. Up here, okay? Now from this, we write the adjoint matrix only. From this, we write the adjoint matrix. Therefore, A inverse equal to adjoint of A by determinant of A equal to 1 by determinant of A is minus 5 into 3 by 3 matrix adjoint matrix. We write the elements of this 3 by 3 matrix. For this 3 by 3 matrix, we require 3 rows and 3 columns. 3 rows and 3 columns. The first row of this adjoint matrix is given by the first 2 rows. From the first 2 rows, we can obtain the first row of adjoint. From the middle 2 rows, we can obtain the second row of adjoint. From the last 2 rows, we can obtain the third row of adjoint. Along the first row, we require 3 elements. The 3 elements are given by 3 second order determinants. It is the first possibility of second order determinant. It is the second possibility of second order determinant. It is the third possibility of second order determinant only. Right? Now these 3 second order determinants will give the 3 elements of the first row. In this adjoint matrix, we require 3 rows. The first row is given by first 2 rows in this matrix only. From the first 2 rows, we consider 3 second order determinants only. The first possibility of second order determinant is like this. Now determinant of this 2 by 2 matrix is 9 minus 2, 7. 9 minus 2, 7. Next. The second possibility of second order determinant. 8 minus 9 minus 1. Next, third possibility. From this third possibility, the determinant of this matrix is 3 minus 12. 3 minus 12. That is minus 9. Now these are the elements. Again, repeat. From the first 2 rows of this fourth order matrix, we can obtain the first row of adjoint only. From the first possibility, determinant is 9 minus 2, 7. From the second possibility, 8 minus 9, minus 1. Third possibility, 3 minus 12, 9. That is minus 9. Next, second row. The second row of adjoint is given by middle 2 rows. Like above, we consider 3 possibilities only. It is the first possibility of determinant, second possibility of determinant, third possibility of determinant. From the first possibility of 2 by 2 matrix, the determinant is 1 minus 12. 1 minus 12 is minus 11. Minus 11. Next, middle possibility. 3 to 6 minus 4. 6 minus 4, 2 only. Next, third possibility. 16 minus 2. 16 minus 2, 14. Next, Already 2 rows are known. Next we require third row. The third row is given by last 2 rows in the fourth order matrix only. From these 2 rows, we consider 3 second order determinants only. The first possibility of second order determinant is like this. 8 minus 3, 5. Next, second possibility of 2 by 2 matrix, 3 minus 4 minus 1. Next, last possibility, 4 minus 12 minus 8. That's it. This is the adjoint matrix into 1 by determinant is inverse of the matrix only. It is a method of finding the adjoint matrix for 3 by 3 only. And this method of writing the adjoint matrix works only for 3 by 3 matrix. This method of adjoint doesn't work for any higher order matrices. This method is only for third order matrix only. Okay. Some are saying that I took the wrong numbers. Once again verified. Let us verify this. Okay. From the given matrix, the first row is 2, 3, 4. Second row is 4, 3, 1. Last row is 1, 2, 4. Okay. Here I took the wrong number. In the given matrix, here it is 3 only. It is a problem. Okay. Let us take this as 4. If we take this 4, this will change only. Okay, let us do this problem by taking the 4 here. So first middle row, same elements, 4, that is 3, 1, 4, 3. Okay. Next last row, 1, 2, 3, 4 like this, 2, 4, 1, 2, 1, 2, 4. This is 4. I am correcting this. This is 4, 2, 4, 1, 2, 1. Okay. Next, 3, 4, 2, 3. Okay. 3, 1, 4, 2. So this is 3, 1, 4. Here I wrote wrong. No. This is 3. I'll correct this. From the given matrix, I wrote here 3, and also here I wrote wrong number. Now I corrected this. From this, we write the elements only once again. Let us check it. This 4 by 4 is correct or not? Now the 4 by 4 is correct or not? Check it on. Is it okay? Yes, right. Now this is correct matrix for given matrix. Okay. We write the adjoint matrix on. First element is 12 minus 2. 3, 4 into 12 minus 2. 12 minus 2. This will change. Okay, we change all this. -2 10. 8 minus 12 minus 4. 8 minus 12 minus 4. 3 minus 12 minus 9. 1 minus 16 minus 15. 8 minus 4 5. 16 minus 2 14. 8 minus 1 8 minus 3 8 minus 3 5. 3 minus 4 minus 1. 6 minus 12. 6 minus 12 minus 6. Is it now? It is correct. Is it correct or not? Check it only. Yes, this is correct. 6 minus 4. Sorry, 8 minus 4. This is 4. Middle one is 4. 1 minus 16 minus 15. 8 minus 4, 4. 16 minus 2, 14, right? Yeah. Right. Now it is right. Correct answer. It is a method of finding the adjoint and inverse of a 3 by 3 matrix. And this method of finding adjoint works only for 3 by 3. This method of finding adjoint doesn't work for any higher order matrix. So first check the matrix is singular, non-singular. Non-singular, we can add the adjoint matrix and write the inverse. If it is singular, we say that inverse does not exist. Right? Okay. This is about problem number 2. Next, we go to the problem number 3. Third problem. If adjoint of A equal to 3 by 3 matrix with elements minus 18, minus 11, minus 10, 2, 14, minus 4, 4, 5, minus 8. Then the absolute value of the determinant of A is if adjoint A is 3 by 3 matrix, then the absolute value of the determinant of A is the elements are minus 18, minus 11, minus 10, minus 18, minus 11, minus 10, 2, 14, minus 4, 4, 5, minus 8. We are asked to find the determinant of A. If you know the elements of A, we can write the determinant of A value. But elements of the matrix are not given. We are given its adjoint matrix elements. With this adjoint matrix, is it possible to find determinant of A or not? Check it on. With this given adjoint matrix, is it possible to find determinant of A or not? It will be possible whenever the relation exists between determinant of A and determinant of adjoint. If we have a relation between determinant of A and determinant of adjoint, we can add the determinant of A also. Yesterday we have written one note point. For any order square matrix, determinant of adjoint of A n cross n equal to determinant of A power n minus 1. It is the result. Determinant of adjoint of A n cross n equal to determinant of A power n minus 1. It is a relation between determinant of A and determinant of adjoint. So using this relation, we can write the determinant of A only. Now we write the solution. Since determinant of adjoint of A n cross n equal to determinant of A power n minus 1. But we require this result only for 3 by 3 matrix. It is a result for general order, nth order. We write the same thing for 3 by 3 matrix. Just substitute n equal to 3 on. Determinant of adjoint of A 3 by 3 equal to determinant of A power 3 minus 1 equal to determinant of A power 2 only. Using this result, if any one is known, we can find other one. If you know the elements of A, we can add the determinant of adjoint. Or if you know the elements of adjoint, we can add the determinant of A, any one. But here we are given adjoint matrix elements. So using the adjoint matrix elements, we write the determinant of A only, which implies determinant of A square equal to determinant of adjoint of 3 by 3 matrix. Minus 18, minus 11, minus 10, 2, 14, minus 4, 4, 5, minus 8. Now find the determinant of this, which implies determinant of square equal to. Now what is the value of the determinant of adjoint? What is the value? I'm writing the value, just check it out whether it is correct or not. Right, 2116. It is square of 46. So determinant of A square minus 46 square equal to 0. This is just like A square minus B square form. So A plus B into A minus B, then it will have two roots, which implies determinant of A equal to, determinant is constant only, determinant of A equal to plus or minus 46. But we are asked to find the absolute value of the matrix A only. Absolute value means plus 46. Therefore, the absolute value of the determinant of a given matrix A3 by 3 is plus 46. Here determinant of a square equal to 46 square only. So determinant of A equal to plus or minus 46 only. So the possible values are plus 46 minus 46 only. And the absolute value means plus 46 only. Suppose if we have here complex number like this 4i, then absolute value means we take the modulus of this, that is 0 plus i4. Because of this number, we take the absolute value, that is modulus of 0 plus i4 means under root of x square plus y square. That is absolute value. Okay, this is about third problem. Next, we are going to problem number 4. The first problem, second problem, both are 2 marks gate questions only. First problem is a 2 marks gate question. Second problem is a 2 marks gate question only. Next, problem number 4. If A equal to 3 by 3 matrix, 2, 0, 1, 0, minus 3, 3, 1, 3, minus 1, and B equal to, again 3 by 3 matrix, 1, minus 1, 0, minus 1, 1, 1, 0, 1, 1. Then determinant of AB minus BA equal to. We are given 2 third order matrices and we are asked to find the determinant of the matrix. Here the matrix is AB minus BA. So first we have to find this matrix AB minus BA and then we have to find its determinant value only. Both are 3 by 3 matrices. Products are possible. First, we have to find the product AB. Next, we have to find the product BA, and then we have to find the difference of these two. After that, we have to find the determinant of these. It is the method. Finding the product AB, BA, and finding the determinant value, it takes time only. It is the actual method only. Now, before going to find the that AB, BA product and finding the difference of these two, first have to check is there any relation or not only among this matrix, among the A, B, and AB minus BA or not. Or we check whether the matrix is symmetric or skew symmetric also. The condition for symmetric is A transpose equal to A. The condition for skew symmetric is A transpose equal to minus A. Yesterday we have written one note point number 6 is about skew symmetric matrix. If it is a odd order skew symmetric matrix, then the determinant of that matrix is 0 only. So we check this AB minus BA is symmetric or skew symmetric. If it is skew symmetric, directly we can add its value only. Not symmetric, then we should find AB, BA, AB minus BA matrix only. Why we are checking this? Here A and B are symmetric matrices only. A and B are symmetric matrices. Just observe the elements of the both matrices only. Observe the elements of both matrices. In A matrix, first row is same as first column, second row is same as second column, third row is same as third column. In the second matrix also, first row is same as first column, second row is same as second column, third row is same as third column. In any square matrix, all the rows are same as columns. All the rows are same as columns. Then such a matrix is called symmetric directly only, without checking the Aij equal to Aji, or without checking the A transpose equal to A. It is a condition for symmetric using matrix notation. Condition for symmetric using element notation. Or directly also by observation, we can say the matrix is symmetric or not. The first row is same as first column. Second row is same as second column. Third row is same as third column. In the second matrix also same. So both A and B are symmetric matrices. That is why we check AB minus BA is symmetric or not. The condition for symmetric is A transpose equal to A. Condition for skew symmetric is A transpose equal to minus A. So if you want to check any matrix is symmetric or not, for this matrix P, we consider P power T. If P power T equal to plus P, symmetric on. If P power T equal to minus P, then the matrix is skew symmetric on. Like this we can check on. If you want to check any matrix symmetric or not, just take the transpose for this and check whether this is equal to plus P minus P only, or not equal to plus P, not equal to minus P only. If it is not equal to P, not a symmetric. If it is not equal to minus P, not a skew symmetric on. Neither symmetric, not skew symmetric on. Okay, first let us check this AB minus BA is symmetric or not. Because of the A and B are symmetric matrices only. Consider AB minus BA. To check this matrix is symmetric or not, we are taking the AB minus BA power T transpose only. Now we apply one of the property of transpose only. According to that property, we are the AB power T minus BA power T on. Since A plus B power T equal to A power T plus B power T. Or without writing this, if this is minus, then it is minus. According to this property, we have written like this, which implies AB minus BA power T. This is equal to, again, we use another property, the transposer product of two matrices only. According to that property, AB whole power T equal to B power T into A power T only. Start with the B, we go back and for each matrix write the transpose. This is a reversal law. B power T into A power T minus A power T into B power T on. which implies AB minus BA power T equal to, from the given data, A is symmetric matrix, B is symmetric matrix. Both A and B are given that symmetric matrices. Because of symmetric, A transpose equal to A. For B matrix also, B transpose equal to B only. So in place of B transpose, we write the B. In place of A transpose, we write A. A, B. Since A transpose equal to A and B transpose equal to B on from the given data. Now observe this. This matrix is not same as this matrix. This matrix is not same as this matrix. So this condition is not satisfied. Therefore, it is not a symmetric matrix. AB minus BA is not a symmetric matrix. Next, if it is not symmetric, we check whether it is skew symmetric or not, which implies AB minus BA power T on. This is equal to, if we take minus outside, then we get the first as AB, second matrix as BA. This matrix is same as this matrix. Totally, this is in the form of matrix transpose equal to minus matrix only. That is, this condition is satisfied. This is satisfied. Therefore, or which implies AB minus BA is a skew symmetric matrix. Is a skew symmetric of order 3. So finally, our given matrix AB minus BA is a skew symmetric matrix, and also it is of order 3. It is a odd order only. Whenever skew symmetric matrix is odd order, then its determinant is always 0 only. Therefore, determinant of AB minus BA equal to 0. That's it is the answer. Actually, we are given two symmetric matrices. A is a symmetric matrix, B is a symmetric matrix. That is why we are checking whether the given matrix is also symmetric or not. While checking the symmetric or not, we check this condition. We do like this only. So the given matrix, this required matrix AB minus BA is not a symmetric, but it is skew symmetric. That is why it is a singular matrix. This is problem number 4. Next, problem number 5. If A and B are symmetric matrices of order 3 by 3, then consider the following S1 colon AB equal to BA, S2 colon AB minus BA is singular. Which of the following is true? Option A, S1 is true and S2 is false. Option B, S1 is false and S2 is true. Option C, both S1 and S2 are true. Option D, both S1 and S2 are false. This is a question, not problem. If A and B are symmetric matrices of third order, then consider the following two statements. In the first statement, the condition is AB equal to BA only. Second statement is AB minus BA is singular only. So we are given two statements and we are asked to check the two statements are correct or only one statement is correct or both are wrong only. The first statement is AB minus BA. The second statement is AB minus BA is singular only. From the fourth problem, that is from the previous problem, we can set the AB minus BA is singular. When A and B are symmetric matrices, AB minus BA is always skew symmetric only. Just go back and check it out. Here A is symmetric, B is symmetric, AB minus BA is skew symmetric only. Because of third order, it is odd order singular only. So this statement is correct. From the fourth problem, second statement is correct. Just you have to check the first statement is correct or not for given two symmetric matrices on. Okay, let us do this problem. Given that A transpose equal to A and B transpose equal to B only. Given that A is symmetric, B is symmetric. So by the definition of symmetric, the condition for symmetric is A transpose equal to A, B transpose equal to B only. This is the given data only. S1. To check the statement AB equal to BA is correct or not, have to check LHS equal to RHS only. To check AB equal to BA or not, we consider LHS separately, RHS separately. We check LHS equal to RHS or not with the given data only. Consider LHS equal to AB. LHS of this statement is AB only. But A is symmetric only. That is why we can replace A with A transpose. Next, B is also given that symmetric. That is why in place of B, we can add the B power T only. According to property of transpose, AB old transpose equal to B transpose into A transpose, or BA old transpose equal to A transpose into B transpose. According to this property, we write these two together as BA whole power T only. So A power T into B power T will be written as BA power T. That's all. No further simplification. We stop here. Again, we consider RHS. We use a given matrices conditions and then we check LHS equal to RHS or not. And RHS equal to BA. We replace B with B transpose, A with A transpose. From B transpose, A transpose, we write this as AB whole power T. Now check whether these two same or not. LHS is equal to BA power T according to given symmetric matrices only. And RHS equal to AB power T. So this LHS is not same as RHS. Here LHS is not equal to RHS. The given data A transpose equal to A, B transpose equal to B, LHS is not equal to RHS. Therefore, S1 is false. The S1 statement is false for given two symmetric matrices. Next, S2. From the previous problem, directly we can say AB minus BA is a singular matrix only. Consider AB minus BA power T. This is equal to AB minus BA power, that is power T power T. This is equal to B power T, A power T minus A power T into B power T. But B transpose equal to B, A transpose A, B. This is equal to minus A, B minus B, A, which implies AB minus BA is a skew symmetric matrix of order 3, which implies determinant of AB minus BA equal to 0. Therefore, which implies AB minus BA is singular. Therefore, S2 is true. Hence, S1 is false, S2 is true. That is option B is correct. Hence, the option B is true. This is about problem number 5. Next, problem number, what is the next number? 6. Sixth problem. The number of different n by n symmetric matrices with each element being either 0 or 1 is option A 2 power n, option B 2 power n square, option C 2 power n square plus n by 2, option D 2 power n square minus n by 2. It is a gate question. Previous gate question. The name of the matrix is symmetric and order of the matrix is n, that is nth order means general order, and we are given two numbers 0 and 1. Using 0 and 1, if we write a symmetric matrix of order n like that, how many number of different symmetric matrices possible? With 0 and 1, how many different symmetric matrices possible. Because of nth order, we never had the nth order symmetric matrix using the two elements. That is not an easy. So here we try to choose the answer by verification because of general order, and the option is given also with the n. So we can choose answer by verification. To choose answer by verification, let us consider the particular order matrix only. And then we choose answer by verification method. Don't write solution. Let us verify this. Suppose if we consider the first order matrix only. I'm taking the first order matrix. The general form of first order matrix is A11. A11. And this first order matrix is containing only one element. And we are given two numbers, 0, 1. Using two numbers, if you write a first order matrix, how many first order matrices possible? Check it first of all. We are given two numbers, 0 and 1. And if you want to write the first order matrix, in this position, we can write the 0 or 1. So we have two possibilities for this. We can write the two possibilities. In place of A11, if you write the 0, we get the 1 first order matrix only. Or in place of A11, if you write 1, we get another first order matrix only. So we can write the two first order matrices using two given numbers only. If you write a first order matrix with the given two numbers, we can get the two first order matrices and check whether these two symmetric or not. First matrix is 0, other matrix is 1. Check whether these two symmetric or not. The condition for symmetric is A transpose equal to A or Aij equal to Aji. But here first order matrix, every first order is symmetric always. Every first order is symmetric because here A equal to 0 matrix. If you take transpose, also we get same matrix only. Suppose A equal to matrix, then A transpose equal to same matrix. That is why every first order matrix is symmetric matrix. N equal to 1, we have taken the first order n equal to 1. For n equal to 1, that is for first order matrix, with the given two numbers, we are getting the two symmetric matrices only. For first order with the given two elements, we are getting two symmetric matrices only. Now this, with this possible to choose answer, we can choose. With this possible to choose answer, we can choose by verification only. In every option, substitute n equal to 1. In every option, substitute n equal to 1 and check any one option gives this 2 or not for n equal to 2 only. For n equal to 1, whether you get 2 or not. Now, first option. First option is 2 power n. If you substitute n equal to 1, this will give 2. Maybe answer. Even though first option satisfies, we cannot stop. We cannot choose this as correct answer only because more than one option may satisfy with this condition. So first option is satisfied. Next, second option. From second option, 2 power n square. If we substitute n equal to 1, this becomes 2. Second option is also satisfied. Next, third option, 2 power n square plus n by 2, n equal to 1. This becomes 1 plus 1 by 2 equal to 2. Satisfied. And last option, n square minus n by 2. And when you substitute n equal to 1, this becomes 0. 2 power 0 is 1. The last option is eliminated. The first three options are satisfied with n equal to 1. So we cannot choose the answer. Then we have to go for next particular order. Next particular order is second order. The general form of second order matrix is A11, A12, A21, A22. And we are given two elements or two numbers, 0, 1. By using these two numbers, if we write a 2 by 2 matrix, then how many number of 2 by 2 matrices possible only? Writing the 2 by 2 matrix is same as writing these two numbers in place of every element only.
Here we can add the 0 or 1. Here we can add the 0 or 1. Here also we can add the 0 or 1. Here also we can add the 0 or 1. For every element, we have two possibilities. We can add the 0 or 1 only. So other way, writing a 2 by 2 matrix with the given two numbers is same as filling up of 4 boxes only. Let us suppose this element is one box, this element is one box, this element is one box, this element is one box. Then writing the 2 by 2 matrix is same as filling up of 4 boxes with the given two numbers only. So we can fill this box either with a 0 or 1, that is two ways. Here also we can fill two ways, because 0 or 1, 0 or 0, 1. Only it is 2 power 2 into 2 into 2 equal to 2 power 4. So if we write a 2 by 2 matrix using two numbers, we can get the 2 power 4 matrices only. This number of matrices, that is 16 matrices only. Out of 16 matrices, all 16 matrices are symmetric or some are symmetric. We have to check it on that. First of all, this number of 2 by 2 matrices possible for given two numbers 0, 1. But we require the symmetric matrices only. The condition for symmetric is A12 equal to A21. For 2 by 2 matrix, the condition for symmetric is A12 equal to 21. A12 equal to 1. These two should be same only. The general form of symmetric matrix of order 2 by 2 is A11, A12, A22, A21. But these two should be same. That is why here we delete this one. Because of symmetric, whatever you write number here, that comes to this position only. You need not to fill this only. Whatever you write, that comes to this one. So you need to find out the maximum possibility for different positions out of 4 positions, and then have to fill that box with it given two numbers on. According to symmetric, these two are same. So the maximum possibility for different elements is only 1, 2, 3 only. Writing the 2 by 2 symmetric matrix is same as filling up of 3 boxes only. For each box, there are two possibilities. Two ways we can fill this box in two ways. So it is 2 into 2 into 2 equal to 2 power 3. Out of 2 power 4, only 2 power 3 are symmetric only. 2 power 3 means here 2, 2, 4 to 8. Out of 16, 8 are symmetric only. So here we have taken n equal 2, that is second order. For n equal 2, we are getting 8 matrices only. For every option, find out the value by substituting n equal 2 only. For n equal 2, the first option is giving the 2 power 2, that is 4. So first option is giving only 4, this is wrong. Next, second option, 2 power n square, 2 power 4. 2 power 4 is 16, this is also wrong. Finally, only one option is left. But we check whether this option gives 8 or not for n equal 2 only. 2 power n square plus n by 2 equal to 2 power. This is 4 plus 2 by 2 only. 2 power 6 by 2, that is 3. 2 power 3 equal to 8. Now satisfied. Out of 4 options, only third option is satisfied for n equal 2 only. For n equal 2, we are getting 8 different symmetric matrices. Here also, this option is giving 8 only. Therefore, C is correct only. That is, for nth order symmetric matrices, this number possible only, using two numbers only. First of all, writing the 2 by 2 matrix is same as filling up of these 4 positions with the given numbers only. That is, for 2 by 2 matrix, 16 2 by 2 possible with the given two numbers. Out of 16 possibilities, only 8 are symmetric only. So filling that is writing a 2 by 2 symmetric matrix is same as filling up of 3 boxes only. So answer is C only. Now we write the solution. Here we have started for first order. We We have started with n equal to 1. That is first order matrix only. For first order matrix, we are getting 2 only. But more than one option is satisfied with this. That is why we are choosing the answer by using other order only. That is second order. For second order also, more than one option satisfied, then we go to third order like this one. Now let us write the solution. We can say A equal to A11, 1 by 1 matrix. Writing the 1 by 1 matrix with the given 2 numbers is same as filling up of this position with the given 2 numbers on. So one box is there. We can fill this with 0 or 1. That is only 2 ways on. Only 2 ways. If it is second order matrix, A11, A12, A21, A22, 2 by 2 matrix. By definition of symmetric matrix, A12 equal to A21. That is why we delete this. We choose these 3 different positions on. You need not to fill this A21. Whatever you write number in place of A12, that will be same as A21 only. So we need to fill only these 3 positions only. In this 2 by 2 symmetric matrix, there are 3 different positions. These 3 may be same, these 3 may be different. Out of 3, 2 may be different only. So maximum possibility for number of different positions is only 3 only. And for each position, there are 2 possibilities. We can fill this box with either 0 or 1. We can fill it with 0 or 1. We can fill this with 0 or 1. So 2 ways, 2 ways, 2 ways. Writing a 2 by 2 different symmetric matrix is same as filling up of 3 elements or 3 positions. There are 3 boxes on. 2 into 2 into 2. That is 2 power 3 on. Next for 3 by 3 matrix. A11, A12, A13, A21, A22, A23, A31, A32, A33. 3 by 3 matrix. According to definition of symmetric matrix, A12 is same as A21. A12 is same as A21. So delete this. A13 is same as A31. Delete this. A23 is same as A32. Delete this only. So out of 9 elements, only 6 elements are left. Out of 6 elements, all 6 may be different. Some may be different only. So out of these 6 elements, the maximum possibility for number of different positions is 6 only. So writing a 3 by 3 symmetric matrix is same as filling up of these 6 boxes only. 1, 2, 3, 4, 5, 6. For each box, there are 2 ways because for each element, there are 2 possibilities only. We can write the A11 as 0 or 1. That is 2 ways, 2 ways, 2 ways, 2 ways like this. 2 ways, 2 ways, 2 ways, 2 ways, 2 ways, 2 ways. 2 into 2 into 2 into 2 into 2 into 2 equal to 2 power 6. Here 2 power 1 equal to 2 1. And so on in general. We can have the nth order matrix. In the first order, 1 different position. In the second order, 3 different positions. In third order, 6 different positions. Like that, if we can find the number of different positions or different elements in this nth order, we can add directly the answer on. By verification, we can choose, or in this way also we can find only. Now say this. In the second order, along the first row, we have 2 elements. Along the last row, we have 1 element. So 2 plus 1, 3 on. In the third order, along the first row 3, along the second row 2, along the last row 1. 3 plus 2 plus 1. Here 2, here 1. So sum of the first two natural numbers, sum of the first three natural numbers, that is 3 plus 2 plus 1, 6 on. There's 6 boxes. Here 2 plus 1, 3 boxes on. In the same way here, in the nth order matrix, along the first row we can find n elements. Along the second row n minus 1, because a12 is same as a21. Out of n elements, if we delete one element, we get n minus 1 only. And so on, 1. Sum of all this is n into n plus 1 by 2. So this number of different positions possible in this nth order symmetric matrix. 1, 2, 3, 4, and so on, like this. N into n plus 1 by 2 only. So 2 into 2 into and so on into 2 equal to 2 power n into n plus 1 by 2 only. For every order, if you observe the final result, 2 power 1, 2 power 3, 2 power 6, 2 power n into n plus 1 by 2 only. For every order, if you observe the value or number, in all these, base is fixed 2, 2, 2, 2, 2. Only the powers are changing depending on order of the matrix only. For first order, power is 1. For second order, power is 3. For third order, power is 6. For nth order, the power is n into n plus 1 by 2 only. From all this, we can say that the base is number of given numbers. The power is maximum number of different positions in the corresponding order symmetric matrix only. This base is same as the number of given numbers, and the power is same as this power is same as number of different elements in symmetric matrix. Because of two given numbers, we are getting the answer as 2 power n into n plus 1 by 2. Suppose if you are given 3 numbers, then answer will be 3 power n into n plus 1 by 2 only. If you are given 4 numbers, then 4 power n into n plus 1 by 2. If you are given 5 numbers, then 5 power n into n plus 1 by 2. If you are given 10 numbers, 10 power n into n plus 1 by 2 only. So base is number of given numbers, the power is number of different elements in the symmetric matrix, or maximum possibility for number of different positions in the symmetric matrix. In this way also we can find, or we can choose answer by verification also. Right? It is a previous gate question only. Next, problem number 7. Next, problem number 7. The number of n by n symmetric matrices the number of n by n different symmetric matrices possible with entries chosen from the set 0, 1, 2, and so on, q minus 1. Is option A, q power n into n plus 1 by 2. Option B, q power n into n minus 1 by 2. Option C, q minus 1 power n square. Option D, q power n square. We can tell the answer also. Now, what is the correct answer for this? Entries means number matrices with matrices possible with entries. Here numbers on. The number of n by n different symmetric matrices possible with entries chosen from the set on. For the matrix, entries means elements only. From this set, we are getting numbers 0, 1, 2, and so on, q minus 1. These numbers only. We are given q numbers only. With the given q numbers, if you write the nth order symmetric matrices, how many possible only? It is similar to previous problem. It is similar to previous problem. In the previous problem, only 2 numbers were given and order is same. But here we are given q numbers only. With the given q numbers, if you write as different n by n symmetric matrices, then how many possible only? You can tell the answer. All are saying that option A, option right. If we go to the previous problem, we have written here general form. Base is number of given numbers. The power is number of different positions in the corresponding order symmetric matrix only. But in the problem number 7, we are given that q numbers. We are given that q numbers and nth order symmetric. So the maximum possibility for number of different positions is n into n plus 1 by 2 only. Just like 2 here q numbers. So answer A is correct. That's all. It is the correct answer. It is similar to problem number 6, but the only difference is number of given numbers only. In the 6th problem, just 2 numbers were given. Here we are given that q numbers only. Number of numbers is q only. It is only difference. Right? So with this problem, inverse of a matrix is completed. Inverse of matrix is completed. This is problem number 6. Problem number 6 and problem number 7 are similar. The only difference is number of numbers only. In 6th problem, 2 numbers are given. In the 7th problem, q numbers are given. It is the only difference. With this, the second subtopic, inverse of a matrix, is completed. Out of 5 subtopics of linear algebra, 2 are completed. One is determinants, other one is inverse. Next, we start third subtopic, rank of a matrix. Next subtopic is rank of a matrix. Next, third subtopic. Rank, comma, linearly independent and dependent vectors. In this topic, first we'll discuss about method of finding the rank of a matrix, and then later we'll discuss about how to check the vectors are independent or dependent on. First we'll discuss about the independence and dependence of the vectors. Now, to find the rank of the matrix, there are three methods. To find the rank of a matrix, there are three methods. First method is submatrix method only. Submatrix or minor of a matrix method. To find the rank of the matrix, there are three methods. Out of three methods, very first method is submatrix method or minor of a matrix method. Next, the second method is echelon form. Second method is echelon form. Next, third method is normal form. These are the three methods. So there are three methods to find the rank of the matrix. First one is submatrix or minor of a matrix. Second one is echelon form. Third one is normal form method. Out of these three methods, the best method, simplest method, easiest method is echelon form. That is why we follow only echelon form method. Whatever the method is applied, we get same rank. If you do the problem by this method or this method or this method, we'll get same rank, no change. That is why out of all this, we choose the simplest method. That is a echelon form method. So we discuss about echelon form method. Now first we discuss about the conditions of the echelon form, and then we read the rank. A matrix A m cross n is said to be, a matrix A m cross n is said to be in echelon form if, after if, we read the two conditions. A matrix A m cross n is said to be in an echelon form if the number of zeros before the first non-zero element in a row is less than the number of zeros before the first non-zero element in a row is less than the number of such zeros. Such zeros in the next non-zero row. The number of zeros before the first non-zero element in a row is less than the number of such zeros in the next non-zero row. Just look at this. Let us suppose these two are rows only. Along the first row, it is the first row, it is second row. Along the first row from left to right, along the first row from left to right, the first non-zero element is 4 because these two are zeros only. It is zero number of zero. We have two zeros. If we have a two zeros in the first row, to satisfy less than condition, to satisfy the less than condition, in the next row, we should have more than 2 only. More than 2. That may be 3, 4, 5 like this one. In the next row, how many zeros are there? 3 zeros before the non-zero number only. So 2 is less than 3 only. In the first row, if we have 2 zeros before the first non-zero number, in the next row, we should have more than 2 only. More than 2 means that may be 3, 4 like this only. But here, 3 zeros are there. So the condition is satisfied. Between the two non-zero rows, between the two non-zero consecutive rows,
sharing అయిపోయింది.
Is it visible or not? Check it. All of you check it. The screen is visible or not? Check it out. Yes. Okay. Now we have started the rank of a matrix. In the rank of matrix, there are three methods. First method is submatrix method or minor of matrix method. Second method is echelon form. Third method is normal form. Out of all this, the simplest, easiest method, best method is echelon form. So echelon form is one method to find the rank of the matrix family. That is why we are discussing the echelon form conditions. A matrix A m cross n is said to be in an echelon form if the first condition. After if, we are writing two conditions. Out of two, the first condition is already written. The first condition is like this: the number of zeros before the first non-zero element in a row is less than the number of such zeros in the next non-zero row. Suppose the rows are like this. Once again, I wrote right there here 0, 2, 0, 4, 0, 7, 2, 3, 0, 0, 5, 8, 0, 2, 5. Let us suppose these two are rows only. Along the first row, from left to right, along the first row from left to right, identify the first non-zero element. First element is 0, second element is 4. This 4 is non-zero number, non-zero element only. From left to right along the first row, the first non-zero element is 4. Before this, how many zeros are there? Only 1 0. Before the non-zero element, that is before the first non-zero element, how many zeros are there? Check it out. Here only 1 0. If we have 1 0 in the first row before the first non-zero number, to satisfy less than condition, in the next row, we should have more than one non-zero element. More than one. More than one means there may be 2, 3, 4 like this only. But how many are there here? 2 zeros. 1 less than 2 satisfied. The condition is satisfied. So this is the first condition only. Between two non-zero consecutive rows, the less than condition should satisfy. The less than condition should satisfy regarding zeros only. Suppose in the second row, if we have two zeros, like this before the non-zero number, in the next row, we should have more than 2 zeros to satisfy less than condition. In the next row, we should have more than 2 zeros. That is, you may have 3 zeros or 4 zeros like this only. One less than 2, 2 less than 4. Between every two non-zero consecutive rows, the less than condition is satisfied regarding zeros. 1 less than 2, 2 less than 4. That's all. Like this, it is the first condition only. Next, condition number 2. The zero rows must be below the non-zero rows. The zero rows must be below the non-zero rows. Zero row means in a row, all the elements are zeros, then such a row is called zero row only. If we have a zero row, that should be placed below the non-zero row only. For example, 0, 2, 5, 6, 7, it is one row. 0, 0, 7, 2, 3, it is one row. Let us suppose 3 rows are like this only. The first row is a non-zero row, second row is a non-zero row, third row is zero row, because in third row all the elements are zeros only. If we have a zero row, it should be placed below the non-zero rows. It is a condition. Or the zero row must be last row of the matrix. We can have more than one zero row. If we have any number of zero rows, all the zero rows must be below the non-zero rows, or all the zero rows must be bottom rows of the matrix only. It is the other condition. If these conditions satisfy, we can say matrix is in echelon form. If it is in echelon form, we write the rank by taking the number of non-zero rows in the echelon form. Using these two non-zero rows, we can write the number of non-zero rows as rank of the matrix only. Next, note point number 1. The rank of a matrix AM cross N is denoted by row symbol, after row symbol within the open brackets A, or small letter R. Here we read this as row of A only. We read this as row of A only. We pronounce this as row of A only. It is a notation of rank of a matrix. Next, note point number 2. If AM cross N is in an echelon form, if AM cross N is in an echelon form, then row of AM cross N equal to number of non-zero rows in an echelon form. Suppose the matrix is in echelon form, then the rank is same as the number of non-zero rows in that echelon form only. So if you are given some matrix to find the rank, first we check the given matrix is in echelon form or not. If it is in echelon form, we write rank by taking the number of non-zero rows. Suppose the matrix is not in echelon form, then we check how to find the rank. That is, we'll discuss the method how to find the rank by echelon form method later. Example. Zero, 4, 7, 2, 0, 0, 5, 2, 0, 0, 0, 3. It is a matrix of order 3 by 4. Now check the given matrix is in echelon form or not. To check the matrix is in echelon form or not, we try to verify the first condition. To verify the first condition, let us start with the first row. Along the first row, identify the first non-zero element. After to write, the first non-zero element is 4. Before 4, how many zeros are there? Check it on. Before first non-zero, we have only one zero element. If we have 1 0 in the first row, to satisfy less than condition, in the next row, we should have more than 1 0. If we have 1 0 in the first row, then to satisfy the less than condition, we should have more than 1 0 in the next row. Here, two zeros are there. 1 0, 2 0. Satisfied. If we have two zeros in the second row, to satisfy less than condition, in the next row we should have more than two zeros only. How many zeros are there here? Three zeros. So between first two rows, the less than condition is satisfied. Next, between second and third also less than condition is satisfied. Regarding zeros, the less than condition is satisfied. In this matrix, there is no zero row. All rows are non-zero rows. So we verify only first condition. For this matrix, the first condition of echelon form is satisfied. Therefore, the given matrix is in echelon form. If it is in echelon form, we write rank directly. Therefore, rank of A 3 by 4 matrix equal to, rank is same as number of non-zero rows. In this echelon form, there are 3 non-zero rows. So its rank is 3 on. Next, example number 2. A equal to 2, 4, 0, 0, 7, 3, 0, 0, 8. 3 by 3 matrix. Again, we check whether the matrix is in echelon form or not. To verify the first condition of echelon form, let us start with the first row. Along the first row, identify the first non-zero number. The first non-zero number is 2 on. Before this first non-zero number, there is no zero. If you don't have zeros in the first row, then immediately we go to the next row. So to verify the first condition, we can start with either first row or second row. If we have zeros in the first row, directly we start with the first row. If you don't have zeros in the first row, then immediately go to the second row. Start with the second row. In the second row also, if you don't have zeros, we cannot check the condition. So we can verify the first condition of echelon form either with the first row or second row. In this second example, along the first row, before the first non-zero, there is no zero. Then we go to next row. Along the second row, the first non-zero element is 7. Before this 7, we have 1 0. If we have 1 0 in the second row, in the next row, we should have more than 1 0. Here, 2 zeros are there. So between these two, less than condition is satisfied. Therefore, it is in echelon form. That is why we can write the rank directly. Rank of A 3 by 3 equal to the number of non-zero rows, that is 3. Next, example number 3. Matrix A equal to 0, 4, 7, 0, 0, 8, 0, 0, 0. 3 by 3 matrix. Along the first row, the first non-zero element is 4. Before this non-zero element, how many zeros are there? Only one row. Only 1 0 in the first row. If we have 1 0 in the first row, then in the next row we should have more than 1. How many are there? 2 zeros are there. In the next row, we should have more than 2. How many are there? 3. So between every two non-zero consecutive rows, less than condition is satisfied. These two are two non-zero rows. Between these two non-zeros, less than condition is satisfied on. And also observe the last row. In this matrix, the last row is a 0 row. If we have a 0 row, we check the second condition also. In the first two examples, there is no 0 row. Directly, the first two matrices were in echelon form according to first condition. If we have a 0 row, we can check the second condition also. According to second condition of echelon form, 0 row exists. That 0 row should be below the non-zero rows. First row is non-zero row, second row is non-zero row, third row is 0 row. This 0 row is placed below the non-zero rows only. The two conditions of echelon form are satisfied. Therefore, it is in echelon form. We write the rank. Therefore, rank of A 3 by 3 matrix equal to number of non-zero rows, that is 2 only. Next, example number 3. not 3, 4. A equal to 0, 0, 0, 0, 0, 0, 0, 0, 0. 3 by 3 matrix. What is the rank of these? According to echelon form, the rank of the matrix is equal to number of non-zero rows. But in this matrix, no non-zero row. All the rows are 0 rows. So rank is 0. Number of non-zero rows is 0. That is the rank of the matrix is 0. Only for null matrix, rank is 0. For not a zero matrix, rank never be 0. For non-zero matrix, rank is non-zero number. For zero matrix, rank is 0. Only for null matrix, rank is 0. For other matrices, rank never be 0. Next, example number 5. Directly in this matrix, only one non-zero row present. Out of 3 rows, only 1 row is non-zero row. In 3 by 3 matrix, we'll have 3 rows only. All 3 rows may be non-zero rows. 2 rows may be non-zero row. 1 row may be non-zero row. These are the possibilities. Out of 3 rows, all the 3 rows may be non-zero rows. 2 may be non-zero rows. 1 row may be non-zero rows only. Suppose if it is an echelon form and 3 rows are non-zero rows, then rank is 3 only. In this echelon form, 2 rows are non-zero rows, rank is 2 only. In this echelon form, only 1 non-zero row, rank is 1 only. All are 0 rows, rank is always 0 only. In this 3 by 3 matrix, only 1 non-zero row is present. Therefore, rank of this is always 1. For any order matrix, single row is non-zero row, then rank is always 1. Except 1 row, all other rows are 0 rows, rank is always 1 only. Therefore, rank of A 3 by 3 equal to 1. Suppose this first row is also 0 row, rank is directly 0 only. So from this we can say that for a non-zero matrix, minimum possible rank is 1. For non-zero matrix, minimum possible rank is 1 only. Examples are computed. Now I am writing here one matrix, just tell me the rank, don't write it. Zero, 2, 4, 7, 0, 0, 0, 3, 5, 0, 0, 0, 0, 5, 2, 0, 0, 0, 3, 0. It is a 4 by 5 matrix, 4 rows, 5 columns. What is the rank of A? What is the rank of this matrix of order 4 by 5? Now, to find the rank of this, first you have to check the matrix is in echelon form or not. If it is in echelon form, we write rank. If it is not in echelon form, we cannot write rank. To verify the echelon form condition, let us start with the first row. Along the first row, before the first non-zero number, we have only 1 0. If we have 1 0, in the next row, we should have more than 1. That is 2, satisfied. If we have 2 zeros in the next row, we should have more than 2. That is 3. If we have 3 zeros in the next row, we should have more than 3. But here, only 3 are there. Therefore, it is not in echelon form. Between last 2 non-zero rows, the less than condition is not satisfied. Therefore, the matrix is not in echelon form. The matrix is not in echelon form. Like examples 1 to 5. The matrix is in echelon form, we write rank directly. Like this, matrix is not in echelon form, we cannot write rank directly. We cannot write rank directly means we may write rank indirectly only. Echelon form, then directly we write rank. Not in echelon form, we write rank. We write the rank indirectly. Indirectly means after reduction. So whenever matrix is not in echelon form, then we try to reduce the matrix A into echelon form. After reduction, we try to write the rank of the matrix. So this is the next note point. We have written these examples for second note point only. Second note point is already in echelon form. The matrix is in echelon form, then we write the rank as number of non-zero rows in the echelon form. Next, third note point is not in echelon form only. The matrix is like this, not in echelon form. For this type of matrices, to find the rank, we try to reduce the matrix into echelon form. For reduction, we apply elementary operations. Note point number 3. Suppose if you are given A m cross n matrix. If you are given A m cross n matrix to find its rank. First, we check the matrix is in echelon form or not. If it is in echelon form, we write rank directly. If it is not in echelon form, we cannot write rank. So in this case, we try to reduce the matrix into echelon form by applying elementary operations. Already we know that there are two types of elementary operations. One is row operation, other one is column operations. Here in the echelon form method, by applying only row operations, we reduce the matrix into echelon form. After reduction, we try to find the rank. We reduce the matrix into echelon form and then we find the rank. Rank of A m cross n equal to number of non-zero rows in echelon form. Number of non-zero rows in echelon form. Right? This is the method of prediction on. But to reduce the matrix A into echelon form, we should apply elementary operations between these two. Like this. Apply elementary operations. By applying elementary operations, we reduce the matrix A into echelon form, and then we find the rank of the matrix. Elementary operation means there are two types of elementary operations, row operations and column operations. But according to echelon form, either we can apply only row operations or only column operations. Either we can apply only row or column. If you want to apply both row and column operations, then such method is normal form method, third method only. According to third method, we should apply both row and column operations. But according to second method, we should apply only either row or column operations. By applying row operations, if we find echelon form, such a echelon form is called row echelon form only. By applying only row operations, if we find echelon form, such a echelon form is called row echelon form. By applying only column operations, if we find echelon form, then such a echelon form is called column echelon form. So we have two types of echelon forms. One is row echelon form, column form. Whatever we apply the method, row echelon form or column echelon form, both will give same rank. That is why in general, we always follow only row echelon form method. That is why here we apply here only row operations. Apply only row elementary operations of it, because we are using the row echelon form method. If you want to use column echelon form, we should apply only column operations. Now, by taking one matrix, I will show you how to reduce the matrix into echelon form. Later, we'll take break. After the break, we will continue this topic. So within 2 or 3 minutes, we'll take break. I'm writing one matrix here of order 5 by 6. with the elements 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, minus 4, minus 2, 7, 9, 5, 6, 3, 10, 2, minus 9, minus 3, minus 2, 6, 7, 13, 14, 2, 1. This is some 5 by 6 matrix. This 5 by 6 matrix is not in echelon form. Just by observing the elements, we can say it is not in echelon form. In this case, if you want to find the rank of the matrix, we try to reduce this matrix into echelon form. To reduce the matrix into echelon form, we should apply only row operations. According to row echelon form, we start with the first column. Consider first column. Along the first column, below the first element, try to make all other elements as zeros. To reduce the matrix into echelon form, let us start with the first column. Along the first column, below the first element, try to make all other elements as zeros. Along the first column, below the first element, all should be zeros. So we try to make these as zeros. For making column elements as zeros, we apply row operations. For making column element zeros, we apply row operations. That is why this method is row echelon form only. After completion of first column, we go to the next column. Along the next column, that is second column. Along the second column, 1, 2, below the second element, try to make all other elements as zeros. Go to next column, along the second column, below the second element, make all other elements as zeros. For making all other elements as zeros, we can use either 2 or 8. By using 2 number, if we make all these as zeros, with this non-zero number, again we get non-zero number here only. That is why don't use the first row. That is, don't use this number only. Try to use the number 8. Using 8, we can make these numbers as zeros only. Because along this row, this first number is 0 only. With this 0, these will not affect only. So from this, we can say that for making the second column elements as zeros, use the corresponding second row. For first column elements, use the first row. After this, we go to the next column, third column. Along the third column, 1, 2, 3. Below the third element, make these 2 elements as zeros only. To make these 2 as zeros, we can use 3 or 9 or 7, any one. But we should not use 3 and 9 because along this row, these are non-zero numbers. With this non-zero number, again, we get here non-zero only. That is why don't use 3, 9. Use only 7, just about this. Along the third column, below the third element, make other elements as zeros by using third row. For making the third column elements as zeros, we use the corresponding third row. Next, after this, we go to the next column, fourth column. Along the fourth column, below the fourth element, all other elements should be zeros. Along the fourth column, 1, 2, 3, 4. Below the fourth element, all other elements should be zeros. To make the fourth column elements as zeros, use the corresponding fourth row only. Just above this element, use this element, make this 0. After this, we go to the next column. Along the fifth column, below the fifth element, all should be zeros if exist. Otherwise, we stop. Along the fifth column, 1, 2, 3, 4, 5. Below the fifth element, no element is present. So we stop here. So we start with the first column and we continue like this until all columns are completed only. For making the column elements as zeros, we are applying row operation. This is called row echelon form only. It is a method of reduction. So if you want to reduce the matrix into echelon form, start with the first column. Below the first element, make all other elements as zeros using first row. Next, we go to second column. In the second column, below the second element, in the second column, below the second element, make all other elements as zeros. For making the second column elements as zeros, use the corresponding second row. For third column, use corresponding third row. For fourth column, use the corresponding fourth row. For fifth column, use the corresponding fifth row, like this. It is a method of reduction only. Later we do the problem on this also. Now we'll take break. The break is 20 minutes. After 20 minutes, we start. Let us take the break. After 20 minutes, we start. And we continue this class. We are taking the break at 7:07. So break time is 20. Then we start at 7:27. Or according to your time, after 20 minutes, we start.
Okay, let us come back to this class. The break is completed. Now till now we have written the 3 note points on echelon form. The first note point is notation, second note point is echelon form, then rank is equal to number of non-zeros. Note point number 3 is for not in echelon form. The given matrix is not in echelon form. We try to reduce the matrix into echelon form by using elementary operations, either only row operations or column operations. If we apply only row operations, then such a echelon form is row echelon form only. According to row echelon form, we try to make the column elements as zeros only. It is a method of reduction up to here before the break. Now let us continue this. Note point number 4. We continue the note points. All the note points are standard results only. Note point number 4. Row of O M cross N. O M cross N is null matrix. The zero matrix is denoted by capital letter O because we use the capital letters to denote the matrices. We use small letters. We use small letters to denote the elements of the matrix. So rank of null matrix is always 0 only. Only for zero matrix rank is 0. For not a zero matrix rank never be 0 only. Next note point number 5. Row of A transpose equal to row of A. Rank of A is same as rank of A transpose. That is A and A transpose will have same rank. 6th. If A not equal to O, A not equal to means A is not a zero matrix, then row of A greater than or equal to 1. Whenever A is non-zero matrix, then rank is greater than or equal to 1. That is, from this we can say that the minimum possible rank is 1. For non-zero matrix, minimum rank is 1. Rank may be 1 or 2 or 3 like this one, but minimum possible rank is 1. 7. If A M cross N not equal to O, then row of A M cross N is less than or equal to minimum of M comma N. For a non-zero matrix, minimum possible rank is 1. And similarly, we can have the maximum possible rank. The maximum possible rank is same as minimum of these two numbers according to order. Suppose if you are given A 3 by 5 matrix, out of these two, minimum number is 3 only. So rank of A 3 by 5 is less than or equal to minimum of these two, that is 3 only. So we can tell the maximum possible rank for any order matrix. Suppose A is 7 by 2 matrix. Its maximum possible rank is 2 only. So rank of A is less than or equal to minimum of these two, that is 2 only. Suppose A is 8 by 1. Minimum of these two numbers is 1. So rank of this is always less than or equal to 1 only. These are the possibilities. Next, note point number 8. If determinant of A n cross n not equal to 0, then row of A n cross n equal to n. Row of A n cross n equal to n only. The matrix is non-singular. Matrix is non-singular. Its order is rank directly only. Suppose A 4 by 4 matrix is non-singular. Then its order is the rank of the matrix. rank of A 4 by 4 equal to 4. That's it. Or if you know the rank also, we can tell the singular, non-singular also, reverse. Ninth one. If determinant of A n cross n equal to 0, then row of A n cross n not equal to n, or row of A n cross n strictly less than n. So whenever the matrix is singular, rank is not equal to its order. Non-singular, rank is equal to order. Singular, rank is not equal to its order. If next point number 10, note point number 10, rank of in equal to, that is row of in equal to, in is unit matrix of order n. Every unit matrix is non-singular because determinant of unit matrix is product of its diagonal elements 1 1 1 1. Non-singular, because of non-singular its order is rank. Non-singular its order is rank. Non-singular its rank is n. Next 11th. Row of AB, rank of product matrix is less than or equal to minimum of row of A, comma row of B. If you know these two individual ranks, we can tell the maximum possible rank for product matrix AB only. For example, A is 2 by 3 matrix. Its maximum possible rank is minimum of these two, that is 2 only. Suppose B is 3 by 5. According to this order, its rank is less than or equal to 3. That is maximum possible rank is 3 only. Between these two, product exists because inner dimensions are same. AB is a matrix of order 2 by 5. Rank of AB is less than or equal to minimum of the individual ranks. Minimum of individual ranks only. But its maximum possible rank is 2. Its maximum possible rank is 3. Minimum of these two will be like this only. 2, 3 only. So rank of AB is always less than or equal to minimum of these two individual ranks only. So rank of product matrix does not exceed the individual ranks only. The rank of product matrix cannot be more than the individual ranks. Always less than or equal to minimum of these two. Either same or less than only. Next point, 12th one. Rank of A plus B less than or equal to rank of A plus rank of B only. Rank of sum is equal to or less than sum of individual ranks only. 13th. Row of A minus B is greater than or equal to row of A minus row of B only. Next, point 14. Every note point is one problem or one question only. You have to remember all these. Or if you know these results, based on this, we can do other problems. Next, 14th point. If, the first point, row of A n cross n equal to n. Rank of A n cross n matrix equal to n. Then rank of its adjoint matrix. equal to n. The second bit, rank of A n cross n is equal to n minus 1. Then rank of its adjoint equal to 1. Rank of A n cross n is less than or equal to n minus 2. Less than or equal to order minus 2 only. Then rank of adjoint of A equal to 0. From these three results, if we can say that if you know the rank of A, if you are given rank of A, we can tell the its adjoint matrix rank according to this standard result. Next, note point 15. If A equal to 3 by 4 matrix with elements K, 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 K. Three by 4 matrix. Then row of A 3 by 4 equal to 1. This given matrix is not in echelon form, but we reduce the matrix to echelon form. According to our reduction method, we start with the first column. Along the first column, below the first element, we try to make these two zeros. While making these two zeros, using this first row, the second and last row, the last two rows will become 0 rows. When these two are 0 rows, only one non-zero row will be left only. That is the rank of this matrix is equal to 1 only. From this, we can set if all the rows are same in any order matrix, all the rows are same or all the elements are same, rank of the matrix is equal to 1 directly. 16th. If A equal to 1, 2, 3, 4, 2, 4, 6, 8, 3, 6, 9, 12, 3 by 4. Then row of A 3 by 4 equal to 1. Here we can set second row is 2 times of first row, third row is 3 times of first row only. That is all the rows are proportional. When all the rows are same, like 15th point, if all the rows are proportional, like 16th point, rank is always 1. So from the last two properties, we can set all the rows are same, rank is 1. If all the rows are proportional, rank is 1. That's it. These are the standard results. Now we do the problems of this. Problem number 1. The rank of a matrix A equal to 1, 1, 0, minus 2, 2, 0, 2, 2, 4, 1, 3, 1 is option A 1, B 2, C 3, option D 4. We require the rank of this matrix. We are given 3 by 4 matrix and we are asked to find its rank. So to find the rank of this matrix, first you have to check the given matrix is in echelon form or not. The matrix is in echelon form, directly we can write the rank. If it is not in echelon form, indirectly we write rank by reducing the given matrix into echelon form. But if you observe all the elements, if this is not in the form of echelon form only. If you observe all the matrix, we can say that the given matrix is not in echelon form only. So let us reduce the given matrix into echelon form according to our row reduction method. In the solution, first write the given matrix A equal to 1, 1, 0, minus 2, 2, 0, 2, 2, 4, 1, 3, 1. 3 by 4 matrix only. To reduce the matrix into echelon form, let us start with the first column. Along the first column, below the first element, we have to make these two zeros. Along the first column, below the first element, we have to make these two zeros. For making column element zeros, we apply row operations. For making row element zeros, we apply column operations. For making column element zeros, we apply row operations. That is, along the first column, using the first element 1, we make other two elements as zeros. The operations will be here like this. R2 position, R2 minus 2 times of R1. First, to make this 2 as 0, here it should be 2 only. To get 2, multiply first row with 2 and subtract the first row with the second row. Subtract the first row from second row. The operation is like this. Multiplication of our first row by 2 and subtracting this row from second row. Next, other element, third row. To make the 4 as 0, here we make it 4 only. To make it 4, multiply first row with 4 and subtract this from last row. R3 position, R3 minus 4 times of R1. With these two operations, we can make these two as zeros. The first row is same, 1, 1, 0, minus 2. Next, operation, R2 minus 2R1. 2, 0, 2, 2, minus 2 times of R1. 2 into 1, 2 into 1, 2, 0, 0, minus 4. Difference of these two. This is second row. This is 2 times of first row. Difference of these two, 0. 0 minus 2, minus 2. 2 minus 0, 2. 2 minus minus plus 4, 6. 2 minus 2, 0 minus 2, 2 minus 0, 2, 2 minus minus plus 4, 6. Next. Similarly, R3 minus 4 times of R1. 4 minus 4, 0. 1 minus 4, minus 3. 3 minus 0, 0. Sorry. 3. 1 minus minus plus 8. That is 9. Now, first column is completed. After completion of first column, we go to second column. Along the second column, below the second element, we try to make this element as 0. Along the second column, 1, 2, below the second element, it should be 0. To make it 0, we apply the row operation. For making the second column elements as 0, we use the corresponding second row only. That is, just above this, use this element minus 2 and make this 0 only. Here the operation will be R3 position. First, make these two same and then subtract or add depending on the sign of the position. Both are having same sign, means subtract. Multiply last row with 2, second row with 3 and subtract. That is 2 into R3 minus 3 into R2 only. It is the operation. One, 1, 0, minus 2, 0, minus 2, 2, 6, 0, 0. 3, 2, 6, minus 6, 0. 2, 9, 18, 3 into 6, 18, minus 0. While making this 0, while making the minus 3 as 0, we are getting totally 0 row only. After completion of second column, we go to third column. Along the third column, 1, 2, 3. Below the third element, no element. So stop here. It is in echelon form. This matrix is in echelon form. So we write the rank. Therefore, rank of A 3 by 4 equal to, from the echelon form, we write the rank by taking the number of non-zero rows. There are 2 non-zero rows. So rank is 2 on. It is the reduction method. From the rank of matrix, we have the problems on 3 by 3 matrix rank, 4 by 4 matrix rank, 3 by 4 matrix rank. But most of the gate questions on 3 by 4 matrix rank. If it is 3 by 4 matrix, and if you want to find the rank, then within 2 steps we can get the rank. Sometimes only within 1 step also we can write rank. While making these 2 elements zeros, 2, 4, directly, this element may become 0 only. In such case, within 1 step we can get rank only. Maximum number of steps is 2, because only we have to make the 2 column elements as zeros. Next, problem number 2. Let A equal to 3 by 3 matrix with elements 3, P, 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 3, P, 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 3 on. We'll stop. If the rank of A is 1, then P equal to. We are given 3 by 3 matrix with unknown P only, and we are asked to find that unknown P value only. To find one unknown, we require a minimum 1 equation. If you want to find the 2 unknown values, we require a minimum 2 equations only. That is why here we require 1 equation. For that 1 equation, already we are given condition like this. We are given condition. Rank of this matrix was already given. With that given condition, we try to get the value of P only. Given that row of A 3 by 3 matrix equal to 1 only. Given matrix is square matrix, and we are asked to find the value of P only. And also given the rank of A equal to 1. Check this order. Here A is 3 by 3 matrix. 3 by 3 means it is a square matrix. Rank of square matrix equal to 1. For a square matrix, if you know the rank, we can say that the matrix is singular or not. Rank is same as order, then non-singular. Rank is not same as order, then singular. So rank is not equal to its order. Therefore, it is singular matrix only, which implies determinant of A 3 by 3 equal to 0. Given that rank of A equal to 1, which implies determinant of A equal to 0. According to the note point. Already we have written the note point. The note point number, this note point number 9. From 8 and 9, using rank, we can say matrix is singular or non-singular. Rank of n cross n equal to n. Rank is same as order, then the matrix must be non-singular only. Otherwise, singular on, like this. So here rank is not same as its order. That is why the matrix is singular. Use the singular condition and find the value of P only, which implies 3 P P P 3 P P P 3. So indirectly we are given equation, and we can solve for P only. If we simplify and expand, by expanding and simplifying, we get the P value. But before going to simplify this, just by observation also we can tell the value of P only. Now observe the first 2 rows. P, P, these two are same. These two are different, these two are different. That is here P, here 3, P only. Suppose P equal to 3, the first 2 rows will become same rows. When 2 rows are same in a determinant, the value of the determinant is always 0 only. So this determinant equal to 0 equation satisfies for P equal to 3 only. Therefore, directly we can tell the value P equal to 3 only. Without expanding, we can set P value according to properties of determinants. That is problem number 2. Next, problem number 3. Let A equal to 0 A B minus A 0 C minus B 0 minus C 0, comma, where A, B, C are non-zero real numbers. Then the rank of A is A equal to 3 by 3 matrix. First row elements are 0 A B. Second row elements are minus A 0 C. Third row elements are minus B minus C 0. And A B C are non-zero real numbers. Non-zero real numbers means this matrix is non-zero matrix. Just go back to the first problem. We'll discuss about something there now. From this matrix we are getting this. From this matrix we are getting this only. Finally, it is the echelon form. Using this echelon form of this matrix A, we are writing the rank of A only. Between these two matrices, don't write equal symbol. Between these two, don't write equal symbol because these two are not equal matrices. If you want to say that two matrices are equal, their orders should be same. Here orders are same. Other condition is their corresponding elements should be same only. Third row of first element is 4. Here third row first element is 0, not same. So that is why these two are not same matrices, not equal matrices. That is why don't write equal symbol here. But this matrix is obtained from this matrix A after applying some elementary operations. So this matrix is called equivalent matrix only, or these two matrices are called equivalent matrices only. If we obtain one matrix from other matrix by applying elementary operations, then the two matrices are called equivalent matrices. Equivalent matrices. That is why between these two, we write the equivalence symbol like this. Between these two, we write the equivalence symbol. That is why the equivalent matrices will have same rank. Rank of this matrix is equivalent to rank of this. That is why rank of A equal to 2 only. Rank of A is same as rank of its echelon form only. Next, we are going back to problem number 3. Like first problem, we need to find the rank of A. Now here we try to find the rank of A by using echelon form method only. Let us write the given matrix. Given A equal to 0 A B minus A 0 C minus B minus C 0. It is a given matrix. It is a 3 by 3 matrix. Because of 3 by 3 matrix, out of 3 rows, all 3 rows may be non-zero rows. All out of 3 rows, all 3 zeros, that is all the rows may be non-zero rows, or 2 may be non-zero rows. Only 1 may be non-zero row. So rank possibilities are 3, 2, 1. Rank may be 3 or 2 or 1. To find the rank of this matrix, we try to reduce the matrix into echelon form. To reduce the matrix into echelon form, we start with the first column. Along the first column, below the first element, these two should be zeros. To make these two zeros, we use this element, but here it is 0. In the very first column, first element is 0. Without with this 0, we cannot make these two zeros only. That is why along the first column, we should have non-zero number only. Then only we can make these two as zeros only. So to make the first column elements as zeros, first we try to get here non-zero number. To get non-zero number, interchange the rows, either first row to second or first row to third row, any one only. Let us interchange the R1 and R2 so that we get the first element as non-zero number only. This is equivalent to minus A 0 C 0 A B minus B minus C 0. Now along the first column, first element is non-zero number. Using this first non-zero number, we can make this element as 0 only. We can make this as 0 only. The operation is R3 position. First make these two same and then add or subtract depending on the sign only. To make these two same, we multiply last row with A into R3. Because of the same sign for both, we subtract minus into B into R1. First row is same, minus A 0 C. Second row is 0 A B. Third row AB minus AB minus plus AB. Subtraction of these two, 0. A into C minus 0 minus AC. 0 minus B into C minus BC. First column is completed. After completion of first column, we go to second column. Along the second column, below the second element, it should be 0 only. Along the second column, below the second element, it should be 0. To make it 0, we use it just above this element. For second column, use corresponding second row only. Now the operation is R3 position R3 plus C into R2 only. Both are having AA. C is not there, C is there. So to get C here, multiply second row with C and then add to third row only. Minus A 0 C 0 A B 0 minus AC plus AC 0 R3, that is minus BC plus C into R2 BC is also 0. Second column is completed. After completion of second column, we go to third column. Along the third column, 1, 2, 3. Below the third element, no element. So stop. It is in echelon form. Therefore, rank of A 3 by 3 equal to number of non-zero rows is 2 only. First two rows are non-zero rows only. So whenever the first element in the first row, is 0, we try to get non-zero number by interchange of rows like this, so that we can make all other elements as zeros. Rank is 2 only. Whether you have observed or not, given matrix is skew symmetric matrix and its order is 3. It is an odd order skew symmetric matrix. That is why it is always singular. Because of singular, rank of this is not equal to its order. That's why here rank is 2 only. Next, problem number 4.
Fourth problem. Suppose that A n cross n is upper triangular matrix. Upper triangular matrix such that I equal to 0, comma, I equal to 1, 2, 3, and so on, n. Stop. Then the rank of A power n equal to option A 0, option B n minus 1, option C 1, option D n. It is a fourth problem. Suppose that A n cross n is upper triangular matrix. So we are given nth order upper triangular matrix, and we are asked to find the rank of its nth power. We require the rank of not A n cross n. We do not require the rank of this matrix. We require the rank of A power n matrix only. A power n matrix only. First of all, it is nth order matrix. Finding the A into A square is not an easy. Even if you get A square also, again finding the A power n is not an easy. That is why here we try to choose answer by verification, or we try to write the A power n matrix by taking the particular order matrix only. Let us start with the first order directly we consider the second order matrix. We try to find the rank of second order matrix, third order matrix. By observation of these two, we try to find the rank of nth power of nth order matrix. The matrix should be upper triangular, and one more condition is I equal to 0 for I equal to 1 to n. That is, diagonal elements should be 0 only. First of all, upper triangular means in a square matrix, all the elements below the diagonal are zeros. All the elements below the diagonal elements are zeros. Such a matrix is called upper triangular. And here the condition is diagonal elements also 0 only. So we consider a 2 by 2 matrix, that is 2 by 2 upper triangular, along with the diagonal elements as 0 sum. And we check it on. Suppose A equal to like this. It is a 2 by 2 matrix. According to upper triangular matrix, below the diagonal should be 0. That is, this is 0 only. Next, also given that one condition, AI equals 0 in the given problem. So diagonal element should be 0. Finally, it is only one non-zero number only. It is a matrix A. Second order upper triangular matrix with the diagonal elements as 0 sum. If you want to find the A square, it is A into A. 0, A, 0, 0. 0, A, 0, 0 equal to row, column, 0. First row, second column, 0. Second row, first column, 0. Second row, second column, 0. Equal to 0 matrix. A square equal to 0 matrix. A power 3 equal to 0 matrix. In general, A power n equal to also 0 matrix for second order. Similarly, we try to choose the 1/3 order matrix only. Third order, 1, 2, 3, 4, 5, 6, 7, 8, 9. According to upper triangular, below the diagonal, these three should be zeros. According to given problem, the diagonal elements also zeros only. Finally, these three may be non-zero, or two may be non-zero, one non-zero now. Let us suppose three non-zero numbers. We require the A square, that is A into A equal to 0, A, B.
0 0 C 0 0 0 into 0 A B 0 0 C 0 0 0 equal to row column 0 row column 0 row column 0 into B 0 A into C, that is AC 0 row column 0 row column 0 0 0. This is not equal to 0 matrix. A power 2 is not equal to 0 matrix for third order. Again, we try to write A power 3, A square into A. A square is 0 0 AC 0 0 0 0 0 0 only. Into A 0 A B 0 0 C 0 0 0 equal to row column 0 first row second column 0 first row third column 0 second row with all other zeros. It is 0 matrix. Now observe the two order matrices. For second order matrix, A power 2 matrix is 0 matrix. For third order matrix, A power 2 is not 0 matrix, but A power 3 is 0 matrix. So in general, we can say that for nth order matrix, A power n matrix equal to 0. That's all. And we require the rank of A power n. Rank of A power n matrix is same as rank of 0 matrix because both are same. Already we know the rank of 0 matrix. So rank of A power n is also 0. So 0 is the correct answer. Right? Like this, if we find the particular order matrix rank, then we can tell the general power matrix rank. Okay, we go back to the problem and we write the solution. Let A equal to 0 A 0 0 be the second order upper triangular matrix such that A I 0. Then A square equal to A into A 0 A 0 0 into 0 A 0 0 equal to 0 matrix, which implies A cube equal to 0 matrix, and so on. In general, A power n equal to 0 matrix for A 2 by 2 matrix. Similarly, next 3 by 3 matrix. Let A equal to 0 A B 0 0 C 0 0 0 be third order upper triangular matrix such that I equal to 0. Then A square equal to A into A equal to 0 A B 0, 0, C, 0, 0, 0, 0, A, B, 0, 0, C, 0, 0, 0 equal to 0, 0, A, C, 0, 0, 0, 0, 0, 0 not equal to 0 matrix, which implies A cube equal to A square into A equal to which implies A power equal to 0 matrix and so on in general. A power n equal to 0 matrix for A 3 by 3 matrix. That is for second order A power 2 onwards all are 0 matrix. For third order matrix A power 3 onwards 0 matrix only. In general for nth order A power n is 0 matrix only. Now for nth order matrix A power n equal to 0. Therefore, rank of A power n rank of 0 matrix that is equal to 0. According to given condition, A power n matrix is 0 matrix. That is where rank of A power n matrix is same as rank of 0 matrix. Rank of 0 matrix is always 0. With this, the 4 problems are completed. We stop here and we'll have a doubt session. We stop the today's class. That is, we stop here today's session, and after this we continue the doubt session. If we have doubts, we can ask. Otherwise, we can take rest, and we continue this topic tomorrow. Hello.
Hello, sir. Hello, sir. At 37 slides, sir.
37.
Yes, sir.
Tell me.
Sir, can you explain the concept once please, sir? That means the reason behind, sir, taking the A mod equal to 0, sir, means determinant of A3 of 3 equal to 0, sir.
Given matrix is square matrix, and one of the element is unknown. In the given 3 by 3, one of the unknown is P, and we are asked to find the P value. To find the one unknown value, we require one equation. We can get that equation with the given rank of a matrix. For this 3 by 3 matrix, rank of the matrix is given as 1, and that too it is a square matrix. For a square matrix, if you know that rank, we can tell the matrix is singular or not according to the standard result note points.
So 36 slides, sir.
34 slide.
36, sir.
No. Look at this first.
Okay. Sorry.
8th node point and 9th node point. Determinant of A n cross n is not equal to 0. Rank of the matrix is its order. Suppose determinant of equal to 0, rank of this is not equal to order, right? Or if reverse, for any square matrix, order is same as rank, the corresponding matrix is non-singular. For a square matrix, order is not same as rank, the matrix is singular. According to this result, we are writing the here. For this given 3 by 3 square matrix, rank is 1. So rank is not equal to its order. Therefore, the matrix is singular. Use a singular condition and try to get the p-value on.
Yes, sir. So at 36 slides, sir.
36. Okay. This one?
So just screenshot, sir.
Which one?
Screenshot, sir. I took screenshot.
Oh, okay. Take it. Okay, completed. Have you taken screenshot? Hello?
Sir, I took screenshot, sir. I took it.
Still, do you have any doubt?
No, sir. No, sir. Thank you,
Okay.
sir.
Hello?
Good evening, sir.
Good evening. Tell me.
Sir, in the echelon, I'm having a doubt in the echelon form.
Okay.
While explaining the echelon form, you said that number of zeros in the upper row should be less than number of zero in the next subsequent row. And for that purpose, you took one example in which the first row was consisting of 2 zeros. And in the now second last problem which we solved, no, sir. It's the second last problem now which we solved. Here the in the first row we are having the element as 0, A and B. So and you said that we cannot have 0 as a first element. So isn't it contradictory?
No. In the first row, actually, directed to check the matrix is in echelon form or not, we start with the first row only. Here the matrix, given matrix is not in echelon form. That is why we tried to reduce the matrix into echelon form. So while reducing the matrix into echelon form, we start with the first column.
So in question 3, sir.
Question 3.
Just second last question. Question 3.
This one. Are you asking about this question? Hello?
No, sir. Question number 3. Next one.
Okay.
It's the second number question. Question number 3. Yes, sir. So here the first element is 0.
Yeah.
So you said that we are R1 goes to R2. We are performing this operation. Exchange of R1. Have any operations like minus A and minus B as 0. That means we can. So is it like a condition like the first element should not be 0 always? Is it condition? Is there any condition like this?
This is only for reduction method only. It is only for reduction. If you want to reduce the matrix into echelon form, we start with the first column. Along the first column, the first element is non-zero element. Then only we can make all other elements as zeros. Otherwise, we cannot make other elements as zeros only. According to reduction method, along the first column, first element should be non-zero number only. With that non-zero number, we can make below that numbers as zeros only. Otherwise, we cannot make the below that elements as non-zero zeros only.
Because in the while explaining echelon form, yes, while explaining echelon form, you took first first element of first row as 0. So that's why I was getting.
No. This is for reduction only. Suppose already zeros are there, we can verify that condition only. Already zeros are given in the matrix. To verify the condition of the echelon form, we start with the first row only. In such case, we consider the zeros before the first non-zero and we compare that with the next non-zero rows. Next zeros only in the next row. But here we are reducing the matrix into echelon form. Hello?
So suppose we are having the upper triangular matrix, so can we say that it is already in echelon form?
Yeah. Every upper triangular
sir.
matrix is in
Now I
echelon
got it.
form, but you have to observe the elements also. Suppose the elements are like this: A, B, C, 0, D, E, 0, 0, F. If A, D, F are non-zero numbers, directly it is in echelon form only. Suppose the matrix is like
Yes,
this:
sir.
A, 0, sorry, particular elements, I write the particular elements. 2, 0, 4, 0, 0, 7, 0, 0, 8. It is upper triangular matrix, but not in echelon form. Are you getting
Yes,
this?
yes, yes, sir.
That is why we can say every upper
Yes,
triangle
yes.
is not in echelon form. Every upper triangular matrix is in echelon form only. So every upper triangular matrix may or may not be in echelon form. If the elements are like this, then echelon form. Elements are like this, not in echelon form. That's why we cannot say every upper triangle is in echelon form only.
Okay, sir.
Okay.
Thank you, sir.
Hello.
Good evening, sir.
Good evening. Tell me.
Am I audible?
Yeah. Yes. You are audible.
Can you please move to 36 slide, sir?
36.
Yes,
Okay.
sir. Here at the bottom of the matrix, all zeros are there now. Zero
Yeah.
rows.
Yeah. Yeah.
Or suppose if that zeros are in the second row and last row 0 minus 2 2 6,
Yeah. Yeah.
then we need to interchange and
Interchange.
tell them rank, or we need to leave like that, sir.
Whatever you said, that is correct. We have to interchange first, and then have to choose the rank by taking the number of non-zero rows only. Because according, if it is the second row is 0 row, third row is non-zero row, it is not in echelon form. According to echelon form, we interchange these two only. That is, while reducing the matrix in echelon form, sometimes you may get second row as 0 row, third row as non-zero row. In such case, we interchange and then we write the rank.
Okay, sir. Sir, you said you said 2 points. I got confusion and I didn't write them. Can you please tell that, sir? Which one is, singular, non-singular rank of matrix is its order?
Okay, I'll tell you.
That one. Can you please?
Suppose if you are given rank for a square matrix like this. For any square matrix, rank is given. Check this rank is equal to order or not. Rank equal to order for a square matrix, then the matrix is non-singular only. Rank is same as order, the matrix is non-singular.
And that equal to 0, sir? Not equal to 0?
Determinant is not equal to 0. Suppose rank is not equal to its order. Rank of the matrix is not equal to its order. Then in this case, determinant of A equal to 0. Singular. Non-singular, not same, singular. Right.
Okay. Thank you, sir.
Okay.
Thank you, sir.
Next.
Sir, can you please show me slide number 26, sir? I wanted to take a screenshot.
You want this?
26, sir. 26, sir.
26. Okay.
Just a moment, sir.
Oh.
And next slide, sir, please, sir. Thank you, sir. That will be all, sir.
Next is,
thank you, sir.
it's completed.
Completed, sir. Completed, sir.
Okay.
Hello.
Hello. Sir, slide number
Tell me.
24. Sir, slide number 24.
20.
Sir, in the 4x4 matrix, how we take last column 4?
Last column is actually to get this 4x4 matrix. What do? We start with the second row. Then after this, we go to third row. And then we go to the first row.
Okay,
After
sir.
completion of all 3 rows, again we come back to the same starting second row only. For collection of elements, we start with the middle element, we move in anti-clockwise, we come back to the same position. In the same way, for rows also, we start with the middle row and then we come back to the same position again.
Okay, sir. Thank you, sir.
From the second row, we are writing first column. From the next row, we are writing second column. Again, from the first row, we are writing third column. After that, repeat the first as last.
Thank you, sir.
Right. Hello. Hello.
Hello. Sir, 39 slides.
39.
Hello.
Tell me.
39. Thank you, sir. Thank you, sir. Slide.
Okay.
Screenshot.
Next page also. I think. $39, $40.
Hello.
Hello. Hello.
Yes, sir. We have solved one question that number of different n cross n symmetric matrices
Yeah.
with each element
Yeah.
either. Sir, in case of symmetric matrices, if they could have asked about skew symmetric, then sir, we could have considered non-diagonal elements as one box or two different boxes.
No. If you want to form a skew symmetrics, out of all the given elements, one of the elements should be 0. Because for a skew symmetric matrix, diagonal element should be 0 only, always. That is why if you are given 0, 1 along the diagonal, we fix 0. So we never count that number on.
So only non-diagonal element should be counted.
Yeah, that too either above or below diagonal. So in such case, we can
Either
get
above or either below.
below, because above, below elements are same, opposite sign.
So sir, both should be considered, no?
In this way, you can say that 0, 0. This is one element. This is one element. Minus sign.
So
0
it
is
is
fixed
either
element.
or both should be considered.
Both.
Both.
Suppose 0, 1 comma is given. Here we can write 0. That is one possible. If you write 0, here also it is 0 only.
0.
If I write here 1, then it is also 1.
1. Okay. And sir, last question. Sir, in Euclidean form, 0 should be continuous in rows. Like consecutive form should be.
Between two consecutive?
No, sir. I am asking like in first row, if we have like 1 0, 1 0, and in second row, if we have 2 zeros, but their order, but they are not consecutive. They are separated by some non-zero element.
You tell me one matrix, I will tell.
Like 0, 2, 3, 4.
0, 2,
and
3, 4.
0, 3, 0. And 1. Now, sir, is this in Euclidean form? Like
No,
there are
not
2 zeros.
No,
but
2 zeros means only before the non-zero element we have to. For every row, if you take number of zeros, that number of zeros should be before the non-zero number only.
Okay, okay.
In the first row before the first non-zero number, 1 0. In the second row before the non-zero number, 0 only.
Okay.
Not after the non-zero number.
Okay, okay, sir. If there is zero after non-zero number, then it should not be considered.
No, no, we never consider that one. Only
Okay.
before the non-zero number in every row.
Okay, okay. Thank you, sir.
Okay.
Hmm.
Okay. Hello.
Good evening, sir.
Good evening.
Sir, can we have a row operation R1 is R1 minus R1, sir?
R1 position, R1 minus
R1.
again R1. No, no.
Yes, sir. We
That's
cannot
not
have
this.
like this, sir.
We have only no. We have only 3 types of rules: Ri2, Rj, interchange of 2 rows, and R1, that is Ri position, K into Ri like this. Other position is, that is other operation is Rj position, Rj plus K Ri like this only. 2 different rows only. Here the same. That is not possible.
Okay, sir. Thank you, sir.
Hello.
Hello, sir. Am I audible?
Yeah, you are audible.
Sir, can you
can
just
ask.
explain the sixth sum that we did in the starting of the class? Sir? The number of different end-to-end symmetric matrices with each element being either 0 and 1.
Okay. We are given 2 elements, that is 2 numbers, not elements, 2 numbers. And we are asked to find the different nth order skew symmetric matrices only. That is using 2 numbers, if you write a symmetric matrix of order n, like that, how many different possible only. So directly nth order matrix, writing the nth order matrix is not an easy. So let us start with this particular order and we generalize only. Let us start with the first order matrix A11. In the first order matrix, only one element is there only. Now in this first element position A11, we can write either 0 or 1. That is 2 possibilities for this element only. If I write the 0, then I can get the one matrix of order 1. If I write here 1, then we'll get another matrix of order. That's all. No other possibility only. With the 2 numbers, with the given 2 numbers, if we write a first order, we get 2 first order matrices only. And both are symmetric matrices only. So for first order, we are getting 2 different symmetric matrices only. Okay. Next, if we take the second order matrix, A11, A12, A21, A22. It is a general form of second order matrix only. But we require only symmetric. According to symmetric condition, A12 equal to A21. That is whatever you write here number that comes to this position. That is why we never choose this. We choose the 1, 2, 3 only. Because out of these three may be same, may be different, or out of 3, 2 may be same also. So the maximum possibility for number of different positions is 3 only. Or the maximum possibility for number of different elements is 3 only. Because of same, by symmetric condition, it is eliminated. Only 3 positions are there. For each position, 2 possibilities are there, 0, 1. In first element position, we can write either 0 or 1. In the second element position, 0 or 1. Third element position, 0 or 1. So totally, how many possibilities here?
3.
2 ways, 2 ways, 2 ways only. 2 power 3 on, like this. So writing the 2 by 2 symmetric matrix is same as filling up of 3 boxes with the given 2 numbers only. So we can fill this box in 2 ways. We can fill this box 2 ways. We can fill this box 2 ways. That is why 2 into 2 into 2. That is 2 power 3 on. Similarly for 3 by 3 matrix also. 1, 2, 3, 1, 2, 3, 1, 2, 3. A12, A21 is same. So eliminate this. A2, that is A13 equal to A31. This is same as this. We delete this. A23 equal to A32. This is same as this only. So delete this only. So along the first row, the maximum possibility for number of different elements is 1, 2, 3. Because these 3 may be same, these 3 may be different, 2 may be same only. Along the first row, 3 different positions. Along the second row, 2. Along the last row, 1. Total number of different positions is 6. So writing the 3 by 3 symmetric matrix is same as filling up of 6 boxes only. 1, 2, 3, 4, 5, 6 only. So 2 ways, 2 ways, 2 ways, that is 2 power 6 only. 2 power 1, 2 power 3, 2 power 6 and so on. From all this we can say base is same as the number of given numbers. Base is same as number of given numbers and the power is same as the number of different positions in the corresponding order symmetric matrix. Like this we can tell the for nth order also. In the nth order matrix along the first row, the maximum possibility for number of different elements is n. In the next row, n minus 1. In the next row, n minus 2 and so on up to 1. This is same as the sum of the first n natural numbers. That is n into n plus 1 by 2 only. So in the nth order square symmetric matrix, this number of different elements will be there only. And for each element, there are 2 possibilities, 0, 1. So 2 into 2 into 2 into 2, how many times? N into n plus 1 by 2 only. That is why 2 power n into n plus 1 by 2 only. The base is number of given numbers. The power is number of different elements in that order symmetric matrix.
Okay, sir.
Okay.
Thank you, sir.